Really fundamental stuff about light and space.
Mm-hmm. The big ones.
Exactly. The kind of things that, well, it can make you rethink pretty much everything. So that's what this deep dive is all about.
Sounds good.
We're going to explore how light actually, moves and what we even mean by empty space.
Big topics. Where do we start?
Let's jump back, way back actually, to an experiment, one that really turned physics on its head.
Ah, you must mean Michelson-Morley, 1887.
That's the one. So what were they actually trying to do back then?
Well, the idea at the time, the sort of standard thinking, was that light needed something to travel through, like sound needs air or ripples need water.
A medium.
Exactly. They called it the luminiferous ether, this invisible, pervasive substance filling all of space.
Oh, right, okay. So they thought if the Earth is moving through this ether,
Then we should see a difference in the speed of light, depending on whether the light beam was going with the Earth's motion or against it or across it.
like swimming with or against a current, makes sense.
It seemed logical. So Michelson and Morley set up this incredibly clever experiment using interferometry to detect these tiny expected variations in light speed.
Okay, precision stuff. And the result?
Nothing. Absolutely nothing. A null result.
Like nothing, no difference at all.
None that they could detect. No matter which direction they pointed the light or what time of year they tried it, the speed seemed exactly the same.
Wow. That must have been confusing.
Oh, deeply confusing. It completely contradicted the prevailing ether theory. It was a huge puzzle.
So this failure, it actually led somewhere important.
Massively important. This null result, this apparent failure, was actually crucial. It laid the groundwork for, well, for Einstein.
Special relativity, 1905.
That's it. Einstein basically took the Michelson-Morley result at face value and said, what if there is no ether? What if the speed of light in a vacuum is constant for everyone, no matter how they're moving?
That's a radical leap.
Absolutely revolutionary. It threw out the need for an absolute frame of reference, the ether, and completely changed our understanding of space and time.
So the experiment didn't just disprove the ether, it sparked a whole new way of thinking.
Precisely. It was a pivotal moment.
Which brings us right back to one of your questions. If light doesn't move through a medium, what does it move through?
And the answer, thanks to Einstein and building on that experiment, is nothing. Or rather, it doesn't need a medium.
It just goes.
It just goes. Light propagates through the vacuum of space as a self-sustaining electromagnetic wave. It's not like sound, which is a vibration of a medium.
Okay, explain that. Electromagnetic wave.
Right, so think back to Maxwell's equations, even before Michelson-Morley. They described light as interacting electric and magnetic fields.
Fields, okay.
A changing electric field generates a magnetic field, and crucially, a changing magnetic field generates an electric field. They create each other perpetually.
So they sort of leapfrog off each other.
That's a great way to put it. This constant interplay allows the wave to travel through completely empty space, carrying its own mechanism for propagation. At that constant speed.
Around 300,000 kilometers per second, give or take.
Give or take, yes. 299,792,458 meters per second, to be more precise in a vacuum.
Okay, so light makes its own way, but then what about space itself? You asked, is there really such a thing as empty space? It feels empty.
It really does, doesn't it? Just vast nothingness. But quantum mechanics throws a wrench in that simple picture.
Quantum mechanics, always making things weird.
Well, it reveals a deeper reality. Even in the emptiest vacuum, there's something called vacuum energy, quantum fluctuations.
Fluctuations? Like what?
It means pairs of virtual particles, like an electron and a positron, can spontaneously pop into existence and then annihilate each other almost instantly.
Whoa, so empty space isn't really empty, it's fizzing.
In a manner of speaking, yes. It's a sea of potential. There's an underlying activity, even in the absence of real particles. It's not static nothingness.
And aren't there also fields, like gravity?
Absolutely. Gravitational fields permeate space, generated by mass and energy. Electromagnetic fields can exist there too. And don't forget the cosmic microwave background radiation.
The afterglow of the Big Bang.
Exactly. It's faint energy, but it's everywhere. So empty space is more like a stage filled with fields and quantum fizz, rather than a true void.
Okay, my head's spinning a bit now. So if space isn't truly empty, then back to the light question. So isn't light moving through that? Through the quantum stuff in the fields?
That's the logical next step, isn't it? If there's stuff there, surely light interacts with it.
Yeah, it feels like it must be pushing through it somehow.
It's a subtle but really important distinction. Light does interact with these things with gravity, with charged particles it might encounter, maybe even subtly with vacuum fluctuations over vast distances. That's debated. But it's not moving through them like a boat moves through water.
How so?
Because remember, light is an electromagnetic wave. Its movement comes from the internal dance of its own electric and magnetic fields generating each other. It doesn't rely on pushing against an external medium, whether that's ether or quantum foam.
So it exists within this active space, but its propulsion is internal.
That's the good way to think about it. It travels in the vacuum, but not by means of the vacuum, if that makes sense. The vacuum is the stage. Light is the performer moving across it under its own power.
Okay, I think I'm getting that. It's powered by its own oscillating fields, which leads to what forms the electric and magnetic fields? Where do they come from in the first place?
Good question. Fundamentally, they originate from electric charges and their motion. It's all part of the electromagnetic force, one of the fundamental forces of nature.
So like electrons and protons.
Exactly. Stationary electric charges create electric fields around them. If those charges move, they also create magnetic fields.
Ah, okay. Moving charge, magnetic field.
And crucially, a changing electric field also creates a magnetic field, even without moving charges. And a changing magnetic field creates an electric field. That's the key for light waves.
That interconnectedness again, Maxwell's equations territory.
Precisely. They describe this beautiful symmetry, how electricity and magnetism are two sides of the same coin, electromagnetism, and how their interplay allows waves to propagate.
Okay, so fields come from charges. But then, isn't something forming the electric and magnetic field of light? Like when light is just flying through space, where's the charge?
Right, that's a critical point.
Yeah.
Once light is created and propagating, its electric and magnetic fields are self-sustaining. They generate each other, as we said. They don't need a continuous connection back to the original charge.
But something had to create it initially.
Absolutely. Light doesn't just appear from nowhere. It's generated by physical processes involving accelerating electric charges.
Like what?
Think about an atom. When an electron jumps from a higher energy level to a lower one, it accelerates, and it can emit a photon, a packet of light. Or think about the sun. Nuclear fusion involves incredibly energetic, accelerating charged particles producing vast amounts of light. Or even just an antenna broadcasting radio waves that involves accelerating electrons.
So the source needs accelerating charges, but once the wave is launched, it's on its own.
Exactly. The initial kick comes from accelerating charges, which create the initial disturbance, the seed of the wave. But then the wave propagates by its own internal mechanism, that self-perpetuating dance of the E and B fields.
And how does its field sustain itself? It really is just that constant back and forth.
It is. The changing electric field makes the magnetic field. The changing magnetic field makes the electric field. Rinse and repeat, oscillating perpendicular to each other and to the direction of travel.
Like they're locked in this perfect rhythm.
Perfectly synchronized, propagating at the speed of light. That's why light can travel across billions of light years of vacuum without, petering out. Its engine is internal.
Mind-blowing stuff. Okay, now let's throw in the particle aspect. You asked, wouldn't light need to be a particle in order to generate a magnetic field? Because we link magnetic fields to moving charges, like particles.
Ah, wave-particle duality rears its fascinating head. It's a great question, because we do learn that moving charges create magnetic fields.
Right.
But for light, as electromagnetic wave, the magnetic field arises from the changing electric field within the wave itself, not from a moving charge particle. It's Maxwell's equations. Again, they dictate that a changing E field must create a B field, wave or no wave.
So the wave nature explains the fields, but light also acts like a particle, a photon.
Exactly. Photons are the quanta, the discrete packets of light energy. They explain how light interacts with matter, like in the photoelectric effect. But importantly, photons themselves have no electric charge.
Ah, okay. So a photon isn't a little charged ball generating the field.
Correct. The fields are properties of the wave as a whole, arising from their mutual generation. The photon is how the wave's energy is often delivered or detected.
That helps clarify. Now, another point about magnetism you brought up. But a magnetic field is the result of a mass spinning, like the Earth or an electron spin.
Right, and that's also true. The Earth's magnetic field comes from its molten iron core rotating. Electron spin creates a magnetic dipole moment. So spinning charge, or mass associated with charge, does create magnetism.
But that's not what's happening in a light wave.
No. The magnetic field in light is purely dynamic, arising from the changing electric field of the wave. It's not a static field generated by a spinning object. It's an oscillating field that's an integral part of the wave's propagation. Different mechanism.
Okay, got it. Dynamic versus static, sort of. So, shifting gears slightly, you observed, light is measured to be identical no matter distance from origin, this constancy.
That's fundamental. The speed of light in a vacuum is constant, c. And its fundamental properties, like its frequency and wavelength in the absence of interactions, don't inherently change just because it traveled a long way.
So no wear and tear from the journey through vacuum.
In a perfect vacuum, no. It doesn't get tired or slow down. This constancy is a bedrock principle of relativity.
But we do see changes, right? Like redshift.
Ah, yes. The observation isn't quite identical. The speed is constant, but the wavelength, and therefore the frequency and energy, can change. Which leads directly to your next point.
Isn't a redshift a loss in energy of the wave? It looks like it's losing energy if it gets redder.
You're absolutely right. A redshift does correspond to a loss of energy per photon. Longer wavelength means lower frequency, and lower frequency means lower energy for each photon. EHFF, Planck's equation.
Okay, so energy is lost.
Yes, but it's crucial how it's lost. It's not like friction slowing it down or the wave dissipating into a medium. The energy decrease is due to specific physical processes affecting the wave during its journey.
Such as? What causes redshift?
There are three main causes we usually talk about. First, and most famous for distant galaxies, is cosmological redshift.
The expansion of space itself.
Exactly. As space expands over the vast time the light travels, the wavelength of the light gets stretched along with it, like drawing on a balloon and then inflating it.
Okay, stretches the waves out. What else?
Second is the Doppler effect, or Doppler redshift. If the source of the light is moving away from us, the waves get stretched out from our perspective, like the sound of an ambulance siren dropping in pitch as it speeds away.
Makes sense. Relative motion.
And third is gravitational redshift. Light loses energy as it climbs out of a strong gravitational field, like from near a black hole or even just leaving a massive star or galaxy. That energy loss shows up as an increase in wavelength, a redshift.
Okay, expansion, motion, gravity. So the energy loss per photon is real, but it's due to these interactions or effects, not the wave just fading.
Correct, which addresses your follow-up.
Yeah.
Isn't the decrease in energy per photon what you would expect if the wave were weakening?
Yeah, it feels like the same thing. Less energy, weaker.
It seems similar, but the physics is different. A classical wave weakening in a medium often means its amplitude decreases as energy dissipates into the medium. With redshift, the energy per photon decreases because the wavelength got longer due to expansion, motion, or gravity. The wave itself is still propagating. It hasn't necessarily lost amplitude in the same way, it's just stretched. The energy is lower per packet, but the wave structure persists.
That's a really subtle but important difference. Okay, one last mind bender you posed. If space isn't expanding, then what is the loss in photonic energy? Hypothetically, take expansion off the table.
Right. If we didn't have cosmological expansion as the primary explanation for why almost all distant galaxies are redshifted, and more distant ones more so, we'd be in a bit of a pickle.
What could explain it then?
Well, Doppler shifts would still exist. Galaxies have peculiar velocities, random motions relative to each other, so some would be moving away, causing redshift.
But some would be moving towards us, causing blue shift.
Exactly. You wouldn't expect the almost universal redshift we see, especially not the clear relationship between distance and redshift amount, Hubble's law.
What about gravitational redshift?
That definitely happens too. Light climbing out of galaxy clusters or supermassive black holes would be gravitationally redshifted. But again, it doesn't seem sufficient to explain the consistent large-scale pattern observed across the entire sky. You'd need some other unknown mechanism, often called tired light theories, where light somehow inherently loses energy just by traveling.
And those theories have issues.
They generally have trouble matching all the observational evidence, as well as the standard cosmological model, which includes expansion. Things like the detailed properties of the cosmic microwave background, or observations of distant supernovae brightness. So, without expansion, explaining the observed redshifts becomes much, much harder.
Wow. Okay, this has been quite the journey. From an 1887 experiment looking for ether.
To the constant speed of light, self-propagating waves, quantum foam, and the expansion of the universe itself.
We saw light doesn't need a medium. It makes its own way via that electromagnetic field dance.
And that empty space isn't truly empty, but light travels in it, not through it like a medium.
And redshift, while an energy loss per photon, isn't just the wave getting tired, but a consequence of expansion, motion, or gravity.
Absolutely. Your questions really hit on some of the most profound shifts in our understanding of reality over the last century or so.
Hopefully everyone listening had a few aha moments connecting those dots. That self-sustaining field idea, that was a big one for me.
It's elegant, isn't it? So maybe a final thought to leave folks with.
Go for it.
Consider this constant speed of light, c. It's not just a speed limit. It's woven into the fabric of space-time itself. As our view of the vacuum of empty space keeps getting weirder with quantum discoveries, how might that subtly influence our understanding of light's journey, or even gravity, over cosmic scales? What other assumptions might need revising?
More mysteries hidden in plain sight, a lot to think about.